Welcome students to this lecture. In today's lecture, I am going to cover some of the aspects of photon induced reactions and inverse reactions. Okay. So, before that, let me briefly summarize what I have discussed in the previous lecture. You know, every time it is important to remember the purpose of this course, what exactly we are expecting, what we are trying to learn in this course. And as I said, one of the important goals is to understand the energy produced from the stars and the synthesis of elements in the universe and mainly in the stars. Okay. As part of that, it is essential to know the properties of the nuclear reactions which are responsible for the energy production and also nucleosynthesis, right. And when we say nuclear reactions are happening within the stars, which are responsible for the energy production and the nucleosynthesis. What are the entities in this entrance channel of the nuclear reaction? If nucleus 1 and a nucleus 2 in general, when we consider, so reaction is happening within certain temperature range and reaction products are formed. In order to understand the synthesis of various elements, we also should keep it in mind that how many types of reaction can take place. And as I said in the previous lecture, majority of the reactions are induced by charged particles, neutrons and then gamma rays. So, because reactions induced by charged particles, neutrons and gamma rays are responsible for the production of majority of the elements, it is important to know how to calculate the rate of the reactions induced by these particles like protons, neutrons, alpha rays and gamma rays. So, I have discussed initially the charged particles, right. So, whose velocities follow the Maxwell Boltzmann distribution. After that, I discussed neutron induced reaction, right, where the slight dependence of the cross section on the velocity has been included in the mathematical expression. In today's lecture, let us see how to write down expression for reaction rate if it is induced by the gamma rays. Okay. So, these are the contents in today's lecture. I have already discussed the recap and photon induced reactions. So, mainly when I say photons, I am referring to gamma. Already I have started discussing in the previous lecture, and mass fractions and inverse reactions. These are the topics I am going to discuss in today's lecture. Okay. If time permits, I will go for this inverse reactions. Okay. So, what are these gamma induced reactions? In the last lecture, if you remember, I have said radiative capture reaction is denoted by 1 plus 2 giving rise to 3 plus gamma, and photo disintegration reaction is represented by gamma. For the sake of convenience, I am using the same symbols. If gamma interacts with the nucleus 3, 1 plus 2 are formed. Okay. This is called as photo disintegration. So, that means after absorbing gamma, nucleus 3 is undergoing decay, it is undergoing decay. So, keeping this in mind, how to represent the reaction rate? Our goal is very simple and very clear. We have to write down expression for the reaction rate if the reaction is induced by the gamma rays. How to write down the reaction rate for a general nuclear reaction? How to represent the rate of a nuclear reaction? Do you remember? The product of the number densities of the projectile and target and then the reaction rate per particle pair. This gives you the total rate of reaction. Now, here we are discussing about the gamma ray. One of the entities is gamma ray. Then how do you represent the energy dependence of the gamma? Whether it follows the Maxwell distribution? No. Then what kind of distribution gamma rays will follow? So, keeping that in mind, I am going to discuss the reaction rate for gamma induced reactions. Okay. All right. So, rate of nuclear reaction induced by gamma and 3. So, there is a small difference between R and gamma symbol, please be careful here. Number density of nucleus 3 and number density of gamma ray. Okay. And this should be multiplied with velocity of the particle, and in this case what is the velocity of gamma ray? Velocity of light, right. So, I am replacing V with C and sigma, which is a function of energy of the gamma. So, this is the general and fundamental expression for the reaction rate when two entities are involved as part of the nuclear reaction. Now, because it is gamma ray, one of the species is gamma ray, the velocity has to be represented as c. Fine. Now, the cross section of course depends on the gamma ray energy, and in stellar plasma at equilibrium, the number density of gamma is not constant, right, and it depends on the temperature and also on the E gamma at equilibrium in stellar plasma. So, how to rewrite this expression of reaction rate when gamma reacts with nucleus 3? Of course, N3 remains same. Now, this N gamma, because of its dependence on temperature and energy of the gamma, it has to be taken inside the integral, okay, and when you write like that, it looks like this. So, velocity c, number density of gamma, which is a function of E gamma, okay, and sigma also as a function of E gamma and dE gamma. Now, remember here the nucleus 3 is absorbing gamma, it is undergoing excitation, right, it is getting excited. During de-excitation, it is giving different products. So, there is a decay process happening here. So, when there is a decay process, the parameter to quantify is decay constant. So, how do you write the expression for decay constant? Keeping in mind the reaction rate, it looks like this. Okay. So, decay constant when nucleus 3 absorbs gamma ray can be written as lambda absorbing gamma by nucleus 3. This is how I am representing. Nucleus 3 is absorbing gamma, it is getting excited, then it is undergoing decay, and this decay is characterized by decay constant, and that is nothing but rate of nuclear reaction 3 gamma, okay, or gamma 3, you can write in whichever you want, divided by N3, number density, right, that is nothing but decay constant. So, in +2 when you have been taught the half life and decay constant, recollect that basic knowledge, it will be clear to you why I have written like the ratio of rate of nuclear reaction and the number density of nuclei designated with number 3. Okay. Remaining term looks same, like 0 to infinity, velocity c, number gamma, okay, which is the function of gamma, and sigma of E gamma, dE gamma. Now, the goal is how to write down the expression for N gamma or the term dE gamma. How the distribution looks like? See, because the number density of the gamma ray depends on the energy of the gamma ray, but at a particular temperature, how the distribution of number of gamma rays looks like. So, let us take the help of recollect your knowledge of statistical mechanics or the backbody radiation, that is Planck's law. Okay. The number of electromagnetic waves having frequency between nu and nu plus d nu. I hope you remember the formula, right? It looks like this. The number of electromagnetic, energy density, okay, that means energy density of the electromagnetic waves having frequency mu and nu plus d nu at temperature is given by energy density. I am writing here d nu is 8 pi h nu cube divided by c cube 1 by e to the power of h nu by k t minus 1 d nu, right. Now, use E is equal to h nu and then convert this equation in terms of, convert it in terms of not frequency, but E. Okay. Then it looks like energy density in terms of E gamma, dE gamma looks like 8 pi divided by h c cube E gamma cube, okay, e to the power of E gamma by k t minus 1 dE gamma. Okay. And from this, number of gamma rays having energy between E gamma and E plus d gamma can be written as, see, this is what I am looking for from this expression, right. From this expression, I want to expand by taking the N gamma, E gamma and dE gamma. Okay. This is nothing but energy density, already I have written the expression, energy density divided by energy, right, multiplied with d gamma. When you divide energy density with energy, you will get the number density, right. So, that is how it looks like 8 pi h c cube E gamma square e to the power of E gamma by k t minus 1 d E gamma. So, now you have this expression, substitute in the decay constant formula, so that you can write as lambda gamma 3 is equal to 8 pi h cube c square. You can simplify yourself, it is not a big deal, 0 to infinity E gamma square divided by E gamma by k t minus 1. Remaining part is cross section at a particular energy of the gamma and d gamma. As I said initially, most of the photo disintegration reactions are endothermic. Okay? That means Q 3 gamma to 1 2 is less than 0. The lower integration limit actually given by E t is equal to Q value of 1 to 3 gamma of the reaction. Okay? Remember that this does not depend on the stellar density. So, basically in this slide I tried to cover the discussion on reaction rate of gamma induced reactions and the major difference when compared to previous lectures, where I had discussed the neutron induced reactions and before that charged particle induced reactions, which follow the Maxwell distribution. Here the number density of the gamma rays are expressed with the help of Planck's radiation law. So, once you have the idea on the rate of reactions induced by charged particles like protons, electrons or alpha particles or sometimes heavy ions, all these particles comes under charged particles or heavy ions, and then neutrons which have mass but no charge, and then gamma which have no mass and no charge. So, you should be in a position to mathematically express the rate of the reactions when they are induced by these three types of particles. Okay? I hope all of you are familiar, all of you have understood with the mathematical expressions I have discussed. Now, let me cover two basic points connected to the same topic and continuing the cross sections and reaction rate. See, initially we have considered general reaction like 1 plus 2 is giving rise to 3 plus 4, right. And remember the nature of identical and non-identical nature. So, this is the reaction rate, okay, and in order to account for the identicalness, we have used a Kronecker symbol. Okay. If it is now in this sigma v, this is basically reaction rate per pair, and this is the number of pairs of non-identical particles. Now, as I said, the role of experimental and theoretical researchers are to calculate this reaction rate, so that value can be used as an input to find out the abundance of the element or energy produced within some certain types of stars. However, experimentally there are many challenges because of various conditions of temperature within the star. Direct measurements are not possible in all ways. So, whatever energy is available, because majority of the reactions are happening at low energies and it is not possible to have it in our laboratory all the time. So, what people do is you make the measurements at high energies and then extrapolate the cross section to the energies of interest. Of course, this extrapolation induces some kind of uncertainty, but this is one of the challenges in nuclear astrophysics, extrapolation of the cross section. And how to circumvent this problem? By taking some other quantity that I will discuss in due course. Okay. So, here I am trying to say that when you try to find out the reaction rate, it is important to have the value of cross section, and cross section cannot be calculated in all cases. That is where people go for the extrapolation. Okay. And the next point, in stellar plasma, instead of number density, researchers go for another quantity, that is matter density, okay, grams per centimeter cube. How they are related to each other? Number density is related to the matter density. that is grams per centimeter cube. Avogadro number, you can cross check the dimensions on both sides, okay, units, Avogadro number, and this is the mass fraction, and this is the mass in AMU. For example, mass of proton, if I stands for proton, nothing but 1.007825 AMU or U, and mass of neutron is 1.008665 U. Okay. And this can also be written as matter density into Avogadro number. This mass fraction divided by the mass can be denoted as mole fraction, So, in the calculations, sometimes you may come across this word mass fraction. There you should be in a position to relate this mass fraction to the number density, okay, mass fraction to number density via matter density, Avogadro number, and the mass of the nucleus. Okay. So, after this, let me discuss one more thing, that is Maxwell Boltzmann distribution. When we do not consider neutrons or gamma rays, proton induced reactions, alpha induced reactions, or some other particles, all are charged entities. I am ignoring the neutrons and gamma rays for time being. They are fermions, right? And ideally they should follow Fermi Dirac distribution. Why? Maxwell Boltzmann distribution is considered. I repeat the question. When fermions are considered, the distribution of their velocities and energies should follow the Fermi Dirac distribution. But why we are considering Maxwell Boltzmann? Please think about it. This is very interesting. Okay. Here I am giving a couple of hints. I am sure you will build up based on them, and by reading textbooks like Rolfs-Rodney and Iliadis, or some other textbooks or material available on internet, you can have a better idea about the selection of Maxwell Boltzmann distribution. Okay. So, why Maxwell Boltzmann distribution is considered for ions in stellar plasma? So, it is basically non-degeneracy, okay, and the motion of nuclei, they are not in relativistic case, it is non-relativistic case. So, let me give you some important features of this Maxwell Boltzmann distribution. Okay. See, physical conditions in interior of the star, that is density and temperature, they lead to equilibrium, okay, velocity distribution, which is basically Maxwellian. Okay. And here, as I have written earlier, P velocity, okay, is equal to, see, now I am using another symbol for reduced mass, either I can use M12 or mu, you can use anything, okay, mu by 2 pi k T to the power of 3 by T, e to the power of minus mu v square divided by 2 k T, 4 pi v square. Okay. Now, this distribution is basically proportional to E into e to the power of minus e by k T, right. At low energies, what will happen to this probability? It can be drawn like this, okay. P as a function of velocity, when you plot with respect to temperature, is a well known, right. It increases up to certain value and then it decreases asymptotically, right. So, at low energies, that is when energy is less than k T, the function, probability function increases linearly, okay. So, this is proportional to basically E, right. And at high energies, when E is much greater than k T, the function decreases exponentially. So, this is basically proportional to e to the power of minus e by k T, okay, decreasing exponentially and asymptotically. So, these are some of the basics which I want you to understand. Here I am posing one question to you, please handle it carefully. The question is following. See, when nucleus 1 and nucleus 2, they are undergoing nuclear reaction, this nucleus 1 velocity distribution is Maxwellian and nucleus 2 velocities are also Maxwell distribution, right. And when we take the velocity distribution of both nuclei, do not you think the reaction rate should be written as the product of both distributions and we should have double integral? I repeat the question. When nucleus 1, nucleus 2 in large number they undergo nuclear reaction and the velocity distribution is Maxwellian because we are ignoring the neutrons and gamma rays. Do not you think we have to consider the double integral to account for the both velocity distributions? Are we doing some mistake? Please think about it. Okay. So, how this double integration can lead to single integration, which I have been considering in all these lectures, will be clear to you. It is not a very big thing. Okay. Now, after this Maxwell Boltzmann distribution, this is the time to discuss one of the interesting aspect of the nuclear astrophysics, that is inverse reactions. Inverse reactions. Really, these inverse reactions do they take place in the stars? Yes, as I said in one of the previous lectures, when 1 plus 2 can give rise to 3 plus gamma, for example, 3 plus gamma can also give rise to 1 plus 2. There is nothing stops us, there is nothing which can stop us to think like this, fine. And it depends on the Q value. When Q values are positive and energy for gamma is not sufficient, then inverse reaction may not take place, it is okay. But at elevated temperature, when gamma possesses high energy, there is a probability that gamma also can induce reaction. That is what I have discussed, right? Reaction rate representation for gamma induced reactions. Now, the question which I am posing now is following. If we consider a forward reaction like 1 plus 2 giving rise to 3 plus 4 or gamma, or 3 plus 4 giving rise to 1 plus 2, if I consider this as a forward reaction and if I consider this as a reverse reaction or inverse reaction, are they related? By measuring the cross section, for forward reaction, can we get the information about the cross section of a reverse reaction? If yes, how to relate them mathematically? Why it is so important? Please pay attention. Many a times it is not possible to measure the forward reaction, but we want to measure the forward reaction. When I say measure the forward reaction, I want to say that measurement of the cross section of the forward reaction, but practically if it is not possible, and if I will check whether I can perform inverse reaction, reverse reaction. If it is possible, I will go for it, I will measure the cross section of the reverse reaction, then using some mathematics, I will calculate the cross section of the forward reaction. So, in this topic, I am going to cover some of the important features of the inverse reactions. Okay. So, already I have written the inverse reaction, I have given the inverse reaction background. Okay. And for example, now I am ignoring the gamma thing. Okay. I am not considering any gamma thing. I am considering the general case of charged particles, which are in majority within the stars. Okay. So, this 1 plus 2 giving rise to 3 plus 4 when Q is greater than 0. Okay. And if Q value is negative, 3 plus 4 is giving rise to 1 plus 2, Q is less than 0. This will become significant when temperature is high. So, in that case also it is important to measure the inverse reaction. Okay. How we can draw this in terms of compound nucleus? Entrance channel, okay. This is entrance channel. The word entrance channel denotes that nucleus 1, nucleus 2 are undergoing reaction, okay, and a compound nucleus is formed. A compound nucleus is formed in the excited state. Okay. One compound nucleus is formed and no compound nucleus is formed generally in ground state. They are formed in excited state and angular momentum, spin, parity. Of course, from shell model you can designate these values, and I also will discuss this angular momentum and parity concept in next to next lecture. Okay. And the energy of this level is Ax, Ex, and this is basically excited state. Excited state. Now, this compound nucleus in excited state won't stay for long, right? It will undergo some kind of decay. So, this is called as exit channel. Exit channel. that is 3 plus 4 and this is the 0. Now, this is the visualization of a nuclear reaction. Fine. What is the cross section of this nuclear reaction? It is the sum of 4 terms. Each and every term I will explain in detail. Let me write down the complete equation. Reduced wavelength square 1, 2, because 1 and 2 are initiating the nuclear reaction. 2j plus 1, where j is capital J is the angular momentum of the excited state of the compound nucleus, and spin of the nucleus 1 is j1 and spin of the nucleus 2 is j2. I will explain the meaning of this term, okay, do not worry. And this is multiplied with the identical nature, that is I mean if we want to account for the identical nature, we have to use this Kronecker symbol, okay. And then fourth term is some kind of matrix element, 3 plus 4 H2 compound nucleus, okay, and compound nucleus H1 1 plus 2 square. This double indices 1 and 2, they refer to the particles involved in the entrance channel, okay. So, here I am trying to explain how to correlate the cross section of forward reaction to inverse reaction or cross section of inverse reaction to forward reaction. That is the topic of the lecture. For that, I am approaching a way where I am visualizing the nuclear reaction in such a way that 1 plus 2 is giving rise to a compound nucleus. This compound nucleus is in excited state and it is decaying to 3 plus 4. In this process, because it is a quantum mechanical process, right, on how many terms this cross section depends conceptually. So, this is a very interesting and very important thing. You have to understand the meaning of each and every term. Let me start from the first term in this equation, okay. So, what is this pi lambda square? See, when you imagine the cross section, you know the geometrical cross section. I think already I have discussed this, but let me quickly do a review. Geometrical cross section is nothing but pi r square, right. R is basically radius of the projectile or radius of the target. You can use any symbols of your wish. This is a geometrical cross section. But here the reaction whose cross section we are trying to understand is not a classical reaction. It is a quantum mechanical case. So, this has to be replaced with a quantum mechanical related term, reduced wavelength, where lambda is equal to well known formula, reduced Planck's constant square root of 2 m, that is reduced mass you can take, okay, m12, and then energy of the projectile in the lab. You are very much aware of geometrical cross section, the area projected by the target to the projectile. Classical case, it is simply pi r square, where r is the sum of the radius of the projectile and target. However, because it is a quantum mechanical process, this radius term has to be replaced with another term, so that we can take into account the effects of quantum mechanics, and that term is reduced wavelength lambda prime, okay, and lambda in terms of reduced Planck's constant I have written. So, this is the number 1 term. If pi lambda square is more, cross section is more. Pi lambda square is more means in lambda you have h by square root of 2 m e. So, it depends on the energy and of course, reaction mechanism also. For that we have to include some more parameters, and number 2 parameter, that is 2j plus 1, okay. This is a statistical factor, where capital J represents the angular momentum of the excited state in the compound nucleus, and J1, J2 as I said spins of nuclei 1 and 2 in the entrance channel. Now, we know that in quantum mechanics, a state with angular momentum J has 2j plus 1 substates, right, 2j plus 1 substates, and the excited state in this compound nucleus represents the compound state for the entrance channel, where there are 2j plus 1 substates, right. Now, the entrance channel involves a total of how many substrates? 2j plus 1 and 2j2 plus 1. These many initial substrates are there. Now, remember these many substrates are available, 2j plus 1 into 2j plus 2. These many substrates are available for the entrance channel. What is the probability for the particle to get identified in the one of these excited states? It is inversely proportional. More number of states, less probability for the particle to identify. Okay? So, that is where this statistical factor comes into picture. Think more about it. Okay? So, this characterizes the quantum mechanical nature, because nuclei 1 and 2, they have these many substrates, and probability for the excited state of the compound nucleus to identify is more if the number of substrates is less. If the more states are possible, then probability to find it in a particular excited state, particular substrate will be very less. So, that is how this statistical factor comes into picture. So, let us go forward. Number 3. Okay. I hope you are clear for this concept, and number 3 is 1 plus Kronecker symbol delta 1 2. It reflects the fact that cross section is twice, right, for identical particles. Cross section is twice for identical particles in entrance channel, isn't it? Now, if 1 plus delta 1 2 is written in cross section, earlier we have written in the reaction rate formula, do you remember? Now, when you take this cross section having 1 plus Kronecker symbol, it will be cancelled when you write in terms of reaction rate. So, there is nothing to worry, but to take into account the twice value of the cross section, we have to include this term 1 plus delta 1 2. Okay? So, it will be 1 and 0 depending on the identical nature or non-identical nature. Okay? And last term, what is that? But here, coming back to this 1 plus delta 1 2, please remember that particles should not counted twice. Particles should not be counted twice. This care you have to take. Okay? But the cross section doubles, because they cannot be distinguished as projectile and target. Okay? So, to summarize today's lecture, I have discussed the reaction rate for gamma induced reactions, and then mass fraction concept, then something about the Maxwell Boltzmann distribution, and I started discussing the inverse reactions. Okay? And in the next lecture I will continue the concept of inverse reactions, how to relate the cross section of the forward reaction to the cross section of the inverse reaction. Okay? Thank you very much for the attention. Thank you.